Hello everyone, welcome back to the channel. In today's episode, we're diving into the exciting world of robotics to explore a fundamental concept that defines the capability and versatility of robots across a wide range of applications, degrees of freedom. And to make this even more interesting, we're going to focus on a particularly impressive robot, the xArm, created by HiWonder. The xArm stands out in the field of robotics for its flexibility, efficiency, and, above all, its multiple degrees of freedom. But what does it mean to have degrees of freedom in a robot? And how does this affect the xArm's ability to perform complex and detailed tasks? Get ready for an information-packed journey as we explain these concepts and show concrete examples of how the xArm leverages its degrees of freedom to carry out complex and precise operations. Whether your interest in robotics comes from a passion for technology, you're considering integrating an xArm into your operation, or you're just curious about how advances in robotics are shaping the future, this video will surely provide you with valuable insights. So, if you like the content, don't forget to like the video and subscribe to the channel if you haven't already. We're about to delve into some of the most fascinating aspects of modern robotics with the xArm from HiWonder. Let's go! Before diving into the specific capabilities of the xArm, it is crucial to understand a key concept in robotics, the degree of freedom. But what exactly is a degree of freedom? In simple terms, a degree of freedom refers to any form of independent movement that a robot, or in this case, any being, can perform. Take, for example, our head. We can tilt it up and down, turn it from side to side, and lean it towards our shoulders. Each of these movements represents a degree of freedom. In the context of robots like the xArm from HiWonder, degrees of freedom are crucial for determining how and how effectively it can interact with its environment. A higher number of degrees of freedom means more flexibility and precision, allowing the robot to perform complex tasks, from precision assembly to the manipulation of delicate objects. Therefore, when talking about the degrees of freedom of the xArm, we are referring to the different ways in which this robot can move and operate in space, similar to how we can move our head in different directions. This capability allows the xArm to carry out a wide range of tasks with impressive efficiency and precision. Now that we have a basic understanding of what degrees of freedom are, let's explore how the xArm uses this capability to transform industries and facilitate tasks that were previously unthinkable. Next, we'll see in 2 steps how to perform a quick quantitative analysis of our robot. Step 1. Draw the kinematic diagram. The first step in understanding the degrees of freedom of a robot is to draw its kinematic diagram. This diagram is essentially a schematic that shows the components of the robot and how they are connected. Think of it as the robot's skeleton. For the xArm, this involves identifying each of its axes or joints and how they relate to each other. By visualizing these links and joints, we obtain a clear representation of the possible directions and movements that the robot can perform. Step 2. Apply the Grubler equation. Once we have the kinematic diagram, the next step is to apply the Grubler equation. This equation allows use to analytically calculate the degrees of freedom of the robot. The Grubler equation is a mathematical formula that considers the number of links and joints in the system, as well as the constraints that each connection imposes. In more technical terms, the formula is where DOF is the total number of degrees of freedom, N is the number of links, J is the number of joints, and F sub I are the degrees of freedom at each joint. By applying this equation to the kinematic diagram of the xArm, we can precisely determine how many degrees of freedom it has. This is not only fascinating from a theoretical perspective, but is also crucial for designers and engineers looking to optimize the robot for specific tasks, ensuring it has the capability to move and perform operations in the desired manner. Let's solve the example. To begin, we must draw the kinematic diagram of the robot. We will start by identifying the different joints that make it up. In our case, they are all revolute joints. There are no prismatic joints. We will proceed to draw the joints and identify them, as well as the links. With everything identified, we proceed to perform the analytical calculation. It is worth noting that the base is considered as the first link. Let us proceed to calculate. In this case, it will be 6 because we are dealing with a kinematic diagram in space. We have 5 joints. For each robot has, it will provide by its nature 1 degree of freedom. We rewrite the equation and substitute the values. Note that this starts at 1 because we name the first joint as J1. The summation yield a result equal to 5, and the term of lambda multiplied by n, J1, will be equal to 0. Based on the equation and obtaining a result of 5 for the HiWonder xArm robot, we can conclude that the robot has a degree of freedom, DOF, of 5. This means that the xArm can perform movements in 5 independent directions or axes of movement. These degrees of freedom could include, for example, movements up-down, left-right, forward-backward, as well as rotations around various axes. This level of mobility allows the xArm to perform a variety of complex tasks, from precise object manipulations to the execution of automated tasks in controlled environments. And so we our journey today. I hope you found this content both informative and inspiring. If you liked the video, please give it a like and share it to help more people discover it. Don't forget to subscribe to the channel and hit the notification bell so you won't miss any of our future videos. If you have any questions or comments, leave them below. We love hearing from you and are here to continue learning together. Until next time.